Here's a data set, monthly average temperatures from a weather station in Cambridge. This data set records the time step of each reading, of course, and a few other columns like the amount of sun and rain and the number of days with frost in the air. Here's a question we might ask. How have temperatures been changing and what will they be in the future? It's no surprise, after you've seen me banging on about it in the earlier videos in this course, that the answer is use probabilistic modelling. Here's the sort of probability model we might create here. This function takes in the timestamp t and then it computes a sinusoid. Here the sinusoid has amplitude alpha and phase shift phi, and then c controls the level and gamma is a linear slope term, which allows my model to express the idea that temperatures might be increasing, or for that matter they might be decreasing depending on the value of gamma. I also stuck on a noise term, a normal random variable with standard deviation sigma, to be able to describe the noise that we see in the data. I've also drawn in this graph, I've drawn on predicted temperatures with the grey line. This grey line, this is just the sinusoid and straight line parts of the function, doesn't include the noise. Before we go on to fit this, I just want to take a sideways look at what we've just done here and think harder about what the model is helping us to do. The data set doesn't tell us thou shalt treat the temperature as a random variable. That's purely our decision as modelers. Why did we make that modelling choice? Well, the question led us there indirectly. The question asked, how have temperatures been changing and what will they be in the future? What it really said between the lines is, how can we predict the temperature variable on the basis of the t variable? This was between the lines of the question, this separation of the data set into things we're trying to predict versus things we're basing our prediction on. The thing we're trying to predict is called the label or the response variable, and I'll call the list of them y1 up to yn, where n is the total number of rows in the data set. The thing we're using to make predictions is called the predictive variables, or the features, or the covariates. In this question, the only variable I'm using in my model for prediction is t, but I could perfectly well have asked for a model which used several predictors. For example, if I had used data for the entire country and I wanted to predict temperatures on the basis of both timestamp and which weather station we're looking at. I just want to repeat, this separation of the data set into predictors and the label isn't something that's there in the data set. It's a view that we as modelers imposed on the data to answer a particular question. This overall goal of having labels and predictors and trying to fit a function that makes predictions is all there is to an awful lot of machine learning, especially the Kaggle-style competitions with leaderboards of whose predictions are the most accurate. Let's write all this out formally. We'll assume we're given a data set where yi is the label for record I and xi is the predictive variable, or maybe a tuple consisting of several predictive variables. First, we choose a probability model for the label variable. This probability model should depend on one or more unknown parameters theta, which we want to estimate, as well as on the predictive variables, which we know. Let's say the likelihood is likelihood for big Y of little y with parameters x and theta. Next, we'll assume that the data set consists of independent observations of the random variable big Y drawn from this distribution. Independence means that the likelihood of the entire data set is the product of the likelihood of the individual terms. Next, estimate theta using maximum likelihood estimation. This should all feel pretty much like what we did in the last video for generative modeling. Let's just review generative modeling and compare it to what we're doing now. The basic difference is that here in supervised learning we have a data set of pairs xi, yi, whereas in generative modeling we just have unlabeled data x1 up to xn. In both cases, we invent a probability model with some unknown parameters, call them theta, and we'll assume that the records are independent samples. This isn't crucial, by the way. If you believe the records in your dataset should not be modelled as independent, you just need to write down a likelihood function for non-independent random variables. There are lots of examples in the notes for this course, which you can find on the course webpage, but we won't need them until we get to advanced models right at the end of the course. Finally, we write down the likelihood for our probability model. For supervised learning, we have the likelihood for the label y, parameterized by theta and by the predictors, whereas in generative modeling, we just have the likelihood for an observation big X. And the training is exactly the same in both cases. We just use maximum likelihood estimation to fit theta. Just a note on the terminology before we go on and actually do some supervised learning. Another word for supervised learning is regression modeling or classification modeling, depending on whether the label is a number or an enum type. Now, let's go on and do some practical supervised learning. Here's a data set of xy pairs, x and y both numbers, and let's try and fit a straight line model to the data. The model I'm going to use is yi is distributed like a plus beta xi plus normal of naught sigma squared, where sigma is given and a and b are the parameters to be estimated. So this model is a straight line plus a noise term. There's no reason why we couldn't estimate sigma if we wanted to. It just happens that for this particular question, the question setter knows what sigma is, so we're going to treat it as a constant rather than as a parameter. And we'll follow the usual procedure. We write down the model for a single observation, then the likelihood function, then the likelihood or log likelihood of the entire data set, and then we optimize it. The question tells us the model for a single observation. It says that each big Y is A plus B times little x plus normal noise. I've just written it here in two different ways. First, how it appeared in the question. Secondly, as a single normal random variable. The normal random variable is magic. There's a theorem which says that if you start with a normal random variable and add some non-random terms, you end up with another normal random variable. We mentioned this rule early on in the course in section 1.4, and I told you that we'd be using it over and over again throughout machine learning. Next, the likelihood of a single observation, i.e. the probability density function for a normal distribution. One thing I want you to watch out for, don't just look up the formula on Wikipedia and copy it out. The Wikipedia formula does not have a plus bx in it, it has mu, because Wikipedia doesn't know that you are trying to use a normal for this specific straight line fit, so it just gives a generic formula. I've seen that students very often don't make this connection, they just copy out a formula and then they get confused when their algebra doesn't make sense. Next, we'll write out the log likelihood of the entire data set, assuming independence as usual. Again, don't just blindly copy out your formula from the line above. In this equation, we're talking about the data set y1 up to yn, whereas in the line above, we were talking about a generic point. So, in this equation, we need to have the subscripts yi and xi. Lastly, we just optimize over the parameters. We've seen this style of numerical optimization several times already, so I'm not going to go over it again. For this question, you could equally well do the optimization with calculus, and if you're interested in the details, you can see them in the lecture notes on the course webpage. Good. So we've now seen a fully worked out example of supervised learning using a model with normal random variables. The next example will look at a different distribution. This is a data set of stop and search records from police forces in England and Wales. Scotland has its own records and Northern Ireland doesn't report them. The UK Home Office makes available several data sets of police records, including stop and search data. It has been pre-processed to list the number of stops and the number of those stops that led to the police finding something suspicious. Fit the model yi distributed like binomial with parameters xi, p, where xi is the number of stops, yi is the number of stops leading to the police finding something, indexed by I, the police force, and p is the parameter that we want to estimate. The steps are exactly the same as always. First, we'll write down a model for a single observation. This is exactly what the question told us. Next, we'll write down the likelihood function. Y is a discrete random variable, so the likelihood of seeing little y is just the probability that big Y equals little y, and you can look up the probability mass function for a binomial online. Remember, don't just copy out the formula blindly, translate it into the parameters we have here, x and p. Next, write down the log likelihood for the entire data set. We're going to assume that the records are independent, as usual, so the log likelihood of the entire data set is the sum of the log likelihoods of each individual record. We want to maximize this function over p, so we might as well gather up all the non-p terms into some constant, let's call it kappa, and then I've just done a little bit more algebra to tidy it all up. Last, we have to maximize with respect to p, so I set derivative d by dp equal to 0 and solve, and this is the answer that we come up with. Let's just do a quick sanity check on the answer. xi is the number of stop and searches for police force I, and yi is the number of stops where they found something suspicious. So the probability of finding something suspicious in police force I should be just yi divided by xi. So to get the average probability over the entire country, we count the total number of stops, and we count the total number of stops where the police actually found something, and divide one by the other. Perhaps this formula is completely obvious to you, or perhaps your first guess would be to find pi separately for each force and then average the value across all of the forces. It's nice to have a systematic procedure, maximum likelihood estimation, which tells us exactly what we have to do so that there's no doubt. Okay, last example, deep learning for image classification. The MNIST database of handwritten images consists of records XI, where XI is in reals to the 28 times 28. In other words, it's a grayscale image with 28 times 28 pixels. And YI is the digit. That's an integer in the range 0 to 9. Formulate this as a supervised learning problem and train your model. I'm not going to go through the working here. You can find it in lecture notes available on the course webpage in section 3. All I'm going to do now is say there's nothing more to this than exactly the same procedure we've just been using throughout this section of the course. Okay, so this is the end of the first part of the course. We've learned how to put together a probability model and how to estimate its parameters using maximum likelihood estimation. We've worked through examples of unsupervised learning and supervised learning. In the next part of the course, we'll go much deeper into how to create models so that the model can capture the features that you want to measure in your dataset.